Hello everyone. Today we'll be discussing the mathematical model of classical mechanics. What this section would have is lots of definitions and theory which will help us in the remainder of this course. So let me put that down. You have yes. Okay. So what does what does modeling have? It has a few important groups of quantities. So let's see. It's called primitives. Then you have defined entities. Then you have axioms, and lastly you have theorems. Okay, so we'll learn about each one of them. Let's begin with primitives. So we say that the primitive of location is a point. Okay, then you have the concept of length. It is associated with extent. Okay, how long or short something is. Okay, so it tells you basically about the size of a body. Then you have an event. So this is happening, maybe an apple falling over your head, that's an event, okay, or an occurrence. Then you have the primitive of time. Okay, what does time tell you? It gives a idea about the flow of events. Okay, into three forms: past, present, and future. Okay, it also gives you the interval between two events. Okay, for example, the apple falling over your head and you getting up to see what has happened. These are two separate events, and perhaps there is some time difference between these two events. Okay, so that can also tell you the interval between two events, two or more events. Okay, then you are well aware about the primitives of force and moment. Okay, before you have started learning this particular course, you are well aware of what a force and moments are, and just briefly they are about the effort which you apply or the in trying to pull or push something, of the moment consequently is the effort for twisting or bending something by your hand or any other equipment. Okay, so moment is associated with twisting or bending, and force is normally uh, from the most basic definitions about pushing or pulling. So mass is also another primitive. So what this is related to something called the inertia, which you have said. So let me just put the definition. The property of a body due to which an external force is required to accelerate it is called inertia, and the primitive of this inertia is mass. Okay, mass, as you know, also determines the gravitational force between two material bodies. You must be well aware by this sort of a relation between the force. Okay, and then you have the concept or the primitive of energy. Okay, it is in the most basic form the capacity to do work, okay, to make things happen and so on. So these are the definition of many primitives which will be useful for this course. And why is it called a primitive? Because there is no other, I mean, this is the starting point of it all. Okay, this cannot be defined in terms of something else. Okay, so this is the basic starting point over here. So we have a very important primitive left out, and that will play a great role in this course. See, the set of all possible locations is a primitive. Okay, so space is a primitive, and you know what a location is. Okay, the primitive of location is a point. Okay, and using this location you create space, which is basically the set of all possible locations. Okay, let's see what space is. Okay, space is modeled as homogeneous isotropic three-dimensional without gaps. Metric of Euclid. Or the axioms. Euclidean geometry as its property, as its properties. So we will try to understand this definition. Some of these terms we should be able to understand right now. Some will perhaps come up slightly later. Okay. So a space is modeled as a homogeneous. So let's see the meaning of this word homogeneous. This means consisting of one type only. Okay, so if you have, for example, water, and then you put in some pebbles inside it, it is clearly two different materials, and hence it's in a heterogeneous material. Okay, so in homogeneous space or material or any other quantity, you would only have one kind which you cannot distinguish from one another. Okay, for example, if you had water and then you had poured sugar crystals into it and then they would dissolve, this would become sweet water. Okay, which is a homogeneous mixture. Okay, so this is what the word homogeneous means, that it consists of only one type. Okay, unlike this one. Then you have the word isotropic. It means direction independence. Think of a simple example. Say you have this material, say a piece of glass, okay, and this glass is such that it allows 100% of the light to pass in this direction, okay, but it only allows, say, 50% of the light to pass in this direction. Okay, the rest of it does not allow to pass. Okay, so this clearly is a case in which the direction plays a role. Okay, so this is in the most general case called anisotropy or anisotropic. Okay, however, if you had the other case in which no matter what direction you choose, okay, this piece of glass would always allow 100% of the light to pass through. Okay, so the intensity would not reduce at all. Any direction you take, it will transmit all the 100% of the light. So this is called isotropy. This property, I am just giving you an example so that you understand what does direction independence mean. So the property of this will not depend along what direction uh, the light is being transmitted in. Okay, and the meaning of the word three dimensions you already know. In the most common words, to describe this space, you will require the variables x, y, and z considering a appropriate origin. Now, at this point, you may be, say, inside a room. Look up any corner of the room, any floor corner of the room, and please can make that as the origin. Okay. Now, once you make that as the origin, you should be able to visualize a three-dimensional coordinate system over there. Okay, say x, y, and z. Okay, that's your origin clearly. Now, if this room in which you are sitting right now is a space, it is homogeneous. It means that it only consists of one type of material. Let's call that material to be air. Okay, it's an empty room clearly for now. Okay, and it need not be air, it can be anything else, but for now we just take one single kind of material inside it. And then you have isotropy inside it, meaning you want to look at the transmissivity of the light, or forget about transmissivity now. Let's consider that the charges have to pass in x direction, in y direction, or in direction something like this. It will have the same response. Okay, so it will have equal ease or difficulty to pass through this. So that's the isotropic part. And same about, say, heat conduction. If heat had to flow in this room, okay, it would not depend whether the direction is x, y, z, or some other combination of it. It will pass in the same speed. Same for diffusion. Okay, if you take a spray, okay, a perfume at your origin, and you just, okay, and then the amount, the diffusivity of this space which you have, say you are standing at this distance over here and you are standing at the same distance from this somewhere else, you would experience that smell of the perfume at the exact same time if the two distances are same, meaning that the diffusivity is same. It's independent of the direction. Okay, so this direction independence plays a big role in defining what a frame is. Okay, and that's the three-dimensional part. And let's see, it is without gaps. Okay, that's a definition of a space. See, you may have a three-dimensional body like this. Okay, and it may have a gap, say a hole like this. Okay, but in your space, this 3D space, there cannot be any gaps. So you cannot say that inside this space I have this region which is not space. Okay, this is not allowed. You will only call it a space when there is no gap in this. Okay, and then the last point is that with the metric of Euclid, or the axioms of Euclid in geometry as its properties. So every space has a property. We'll learn about axioms in a few minutes, but every space has a property, and this should also have one. You already know one of them. Okay, let's say in this space you have 2 points, this and this. Okay, now the distance between these 2 points is, so if you have the coordinates of one is x1, x2, x3, or x1, y1, z1, the coordinate of the other is x2, y2 and z2. The distance between these 2 points is x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. Okay, this definition of the distance between 2 points comes from this Euclidean geometry or the Euclidean metric. It's actually also called the Euclidean distance between 2 points. Okay, so in mechanics which we will be learning, we only use the definition of a Euclidean space. Okay, when you learn in about mathematics, say linear algebra or courses like that, then you will have lots of different spaces, each having its own properties. Okay, but here in this particular course we'll be constraining ourselves to the Euclidean space or the axioms of the Euclidean geometry, which will be more clear as we progress. Okay, so that's the definition, and this is what a complete definition of a space is. The space is modeled as a homogeneous isotropic three-dimensional without gaps, with metric of Euclid or the axioms of Euclidean geometry as its properties. The other important definition is that a space is absolute. And what was space, if you remember? The set of all possible locations. Okay, that was space. So space is absolute. What does it mean? That it is its properties like distance between 2 points. We are taking this property because we have just shown it. Are independent of the material uh, bodies occupying its locations or moving through it. And also independent of its own motion. We'll dissect it now. The first part says that its properties, okay, right now the only easiest property which we have taken is distance between 2 points, but as you progress and learn more about the subject, you will find out that there are many more properties, but all of this will be true. Will be independent of the material bodies occupying its location. So this room which you have now, the corner is your origin, okay? The bottom corner of this room is the origin. The distance between 2 points which have been marked over here and here is this. Now imagine if this room was not filled with air, but it was filled, say, with concrete or wood, okay, or plastic, completely filled with plastic. But the distance between these 2 points would still remain the same, right? It would really not matter whether air is being filled up over here, or there is concrete, wood, okay, or whole metal is cast into it. The distance between the 2 points remains the same. So that's the first part. Okay. Similarly, it's not just that the material can exist, the material even if it was flowing, for example, now if this room which you have also has windows, okay, and then the air is flowing like this, okay, and tomorrow I hope never happens, but due to a flood or something, the water is now flowing through this, but the distance between these 2 points of this space will always remain this, okay, and hence it is not just independent of the material bodies occupying its location or moving through it, okay. It can be air, it can be water, it can be anything else. The material, the distance between the 2 points remains same. It is also independent of its own motion. Now tomorrow, if this room, okay, was not actually a room, say, but it was a car, okay, that's the ugliest car I can think of, and you have your origin something like this. Now the distance between these 2 points, okay, will remain the same over here even if this car is in motion, because in this space, okay, the distance between the 2 points will be independent of its own motion. So this is how we understand that the space is absolute. Its properties, like the distance between 2 points, are independent of the material bodies occupying its location or moving through it, and is also independent of its own motion. Okay, I hope this is clear. Now let's move on to the next topic. Since we have defined the primitives, we now have to go to defined entities. Okay. Let's see it from the example of time. The Let me come back. So the okay, Newtonian unit of time is defined. This is an important word, okay. We knew what time was, we had some basic, but now we have to quantify it, okay, and for that we need a definition. That's where we are under this topic of defined entities. So Newton unit of time is defined as the recurring interval of an ideal repeatable phenomenon or an experiment, okay. We can also call it a clock. You must have done experiments about, say, the swinging of a pendulum, and then you try to measure using a clock the time period and so on, okay. uh, that's how you understand what time is, okay, and how is it defined as the recurring interval of an ideal repeatable phenomena. So you can just recall that. I'll just write it over here. Recall your school experiment. Okay. So the time period between two events, okay, will always belong to a real number. Okay, it can be 1 second, 2 second, 0.12 second, and so on, or minutes, or whatever you would want to call it. Okay, so you say that time, or it can also be minus 1.2 second, that will tell you about an event of the past. Okay, so time interval between two events is an element of the real number from minus infinity to plus infinity. And it is modeled by real numbers, so you don't use imaginary numbers to talk about time. Okay, now since this is the first definition of time which you have seen, let's move to the other one, that's called reference frame. Again, it is defined, okay, as a space moving in any manner with an observer having a clock. Okay, clock to measure, say, the interval between two events. So a reference frame is defined as a space moving in any manner with an observer having a clock. So this is important, that it is a space, and you know what the space is. You have defined it as a primitive above. It has certain properties which we have discussed in great detail. Okay, so a reference frame must have all these properties. Over and above that, it should also have an observer, which may be you, it may be a computer, but it should have a clock with which it can measure the interval between times using a clock. Okay. So in our mechanics, or the so-called classical mechanics, time is absolute, meaning it is independent of the reference frame, okay, or the presence of or motion of material bodies in this reference frame. Okay, so it is also universal, meaning if you measure the time interval between two events, it will be the same in all reference space, irrespective of the relative motion between the reference frames. Okay, so that's the important part. For example, if you drop uh, an apple while moving inside a car and it touches the floor of the car, okay, the time interval between these two events, that is dropping of the apple and the apple touching the floor of the car, will be the same irrespective of whether you are inside the car or you are on the ground observing this moving car and the events which we have just spoken about. So it is universal, okay, and it is also absolute. If this car had air inside it, you would get the same time between these two events, okay. If the car had only oxygen inside it, you would have the same uh, time between these two events, okay. So that's what the time is, and it's a very important part of how we deal with mechanics. So the absoluteness and the universality of time is very important to how we deal with mechanics, or how we learn about mechanics. Okay, so let's now move and define some of the other quantities. A material body is a collection of matter, mass. See, the mass we have already defined as a primitive before, okay? Please go back and check if you have forgotten how we had defined the mass as a primitive. A material body is a collection of matter whose each point is called a material point. Matter is not continuously distributed over a volume, but is decomposed of very large number of atomic, subatomic particles, protons, neutrons, electrons, and so on. And then there are statistical physics and statistical methods to deal with this, since you wouldn't really know exactly how the electrons are there, at what speed they are moving absolutely. You must be aware of the principles which guide this uncertainty. So there are statistics involved in this. But what we learn is that we don't go to that atomic or the subatomic level and see what's happening. We look at the larger quantities, which are actually a product of what happens because of the motion of these small molecules and atoms and parts within those atoms, okay. So if you remember something like, say, the pressure on a wall is basically these particles which are there in this container, and they hit the wall and then go back, and then there's a force. So pressure is somewhat of a metric on this wall, okay, of this particle going, hitting, and coming back. So there is a clearly a change of acceleration, and hence there is an associated force. So this is the quantity which we look at in our engineering analysis in general, okay. Quantities like the pressure, quantities like the density, okay, and temperature, if you know, they are somewhat related to the motion of the atoms and molecules and how fast they are moving and so on. If the temperature is high, they start moving at very high speeds, so there's a lot of kinetic energy of those atoms. So pressure, density, and temperature are the quantities which we are interested in, and they are the gross effects of the actions of many molecules or atoms. Mhm. Now, we don't want to understand what each atom or each molecule does to the temperature or the pressure or density. Okay, we don't want to, because there are like millions of them, and we don't want to do that, because for most of the things around you in your room, okay, say your mobile phone, your desk, the walls, the bulbs, okay, the lights, the pens around you, the number of atoms and molecules are huge. So we don't want to deal with each one of them separately. Okay, hence we do some sort of an averaging. Okay, and we want to do that using this concept called the continuum. Okay, continuum hypothesis. So let's see the motivation behind it. First of all, let's call this as your material body. Okay, and each point of this is called a material point, so let's call this as the material point. Okay, there are many other material points, but I am referring to this one specific material point right now. Now, what is the motivation? To study the average of an entity in the small neighborhood okay, to study the average of an entity in a small neighborhood of a material point. So if you have this material point and you have this small neighborhood of this material point, and you want to study about, say, the pressure or the density or the temperature, okay, in a small neighborhood of this material point, you require something called the continuum hypothesis. Mhm. So we postulate a continuum hypothesis. Okay, what is this hypothesis? There exists a hypothetical distribution of mass and other non-inertial properties over the volume of a given body with a volume density. Okay, so let's see the postulate. There exists a hypothetical distribution of mass. Okay, meaning if this is the material body, I've tried to draw it as close as it can to the previous one. Okay, there exists a distribution of mass, meaning if you have this coordinate of x, y and z, okay, you have this mass distribution, let's call it mass distribution, which is a function of x, y and z. So at any given point, material point like this, okay, if you know the coordinates of that material point, the mass density, okay, can be said to be whatever be the function. I mean, maybe it is x square plus y square plus z square, just the easiest function I could think of, okay. And what is the postulate? The postulate is not that it is there in it is reality, but that it is to exist, okay. We have to assume that such a mass density exists, mass distribution exists, and not just the mass distribution, it can be any other non-inertial property as well. So so mass, as you know, is associated with the inertia. Now can you think of an example? Anything in red which I write, okay, that's something which you should be able to answer yourself. If you are not able to, you have to think about it and then answer. Okay, and these distributions have to exist over the volume of the given body with the volume density. Okay, so that's the overall idea. And now with this there is this continuous function which will exist, mass density function, or maybe a temperature distribution also can exist, right? That a temperature also can exist as this, and then it can have some other function to define what the temperature would be at each material point. So this is the sort of averaging. This mass density and this temperature has come out at this material point, okay, by averaging a small neighborhood around it. So the contributions and the motions of the atoms and molecule in the small neighborhood contribute to this mass distribution or the temperature or the pressure and so on. Okay, that's the part, that's the important part over here. Okay, so this idealized, this is not real, okay. You know that every rigid body or even deformable body around you, okay, or a fluid body, say water kept in your bottle or glass, it's all made up of very small particles. But to assume this averaging, this continuity, okay, makes it an idealized situation for us, okay. So we say that such an idealized continuous distribution of matter is called in which exist material points. Okay, we have seen what a material point is. Okay, you have to have material curves, material surfaces, Material volume elements. Okay. So the words are important. It is an idealized continuous distribution, okay, for say the mass distribution, okay, is called a continuum in which exist the material points, material curves, material surfaces, and material volume elements. We'll see each one of them in a few minutes, okay. And one of the things which you should be very convinced right now, that despite the fact that we make this idealization, okay, that we ignore the distributions of atoms and molecules and see these averaged quantities around the material points, the answers which are given as a result of the mechanics or the thermodynamics of it, okay, is physically valid. Okay, so it has been shown to be valid in the real world for a long time and for lots of situations. There are, yes, few exceptional situations of engineering applications where such a continuum hypothesis may not work, okay, but for most of the cases it works, and that will be the part of study of at least our course. Perhaps later on, if you take up some course in molecular dynamics or quantum mechanics and things like that, you would be able to see those special cases where the continuum hypothesis breaks down and it's no longer valid. But most of the engineering applications around you, I can assure that this idealization of a continuum works reasonably well. Okay, so let's just first draw some diagrams. So this is part 1 of this body B. So let me just write this down as body B. This is part 2. This is part 3. This is part P. Okay. Let me also claim that this is a material point Q. Okay, it's not the only material point, or these are not the only parts, right? There can be many parts, big, small, of different sizes. And this body B has a volume B. It has this surface B. Okay, you can take out a small part of it, a finite part of it. Okay, it's not infinitesimal for now. Okay, so this is a finite part P. This will also have a volume. This will also have this surface, or you can have an infinitesimally small part. I don't know, P3. P3 is this infinitesimally small part. Okay, and it will have its own DVP and DSP or whatever you want to call it. Okay, so now let's relook at what we have just learned. Such an idealized continuous distribution of matter is called a continuum in which exists material point. Check, okay, the red which you can see is a material point, and there has to be infinite material points. Okay, it's not the only, I've just shown it as one. Material curves. Okay, so then you have these boundaries and surfaces which are called the material curves and the material surfaces. Okay, this is the boundary of this. Okay, and the surface of a continuum material is not something very hard for you to see. Look at the phone or the table or your laptop around you. Okay, you can clearly see its curves and surfaces. And then it also has material volume elements. These volume elements have been shown in green color, which are parts, part 1, part 2, part 3, part P, and many other parts. The parts of these volumes can be finite or it can be infinite. Okay, they can be big, they can be small, whatever it is. Okay, so this is the reason, and you can clearly think of that. I mean, all these parts eventually make up this whole volume. Okay, so let me now move to another definition. So your knowledge of this calculus will be very helpful. Actually, not just helpful, it will be necessarily needed. So you will come across some terms which you have learnt in your calculus either before or you are learning it right now. We're not sure. Okay. In this model, in this mathematical model, defined entity whose configuration VP Okay, so let's see this mathematical model in terms of the diagram which we have drawn, which was itself an idealization. So in the mathematical model, a body or a material body or a mechanical system or a system B. Okay, so the B which you see in this diagram, okay, is can be anything. It can be a material, it can be a body, it can be a material body or a mechanical system. Okay, by a system it can be like a whole machine in itself. Okay, or a system B is a collection of matter of well-defined identity. Okay, I have shown you some of these well-defined identities like the parts P1, P2, P3 and so on, whose configuration at a given time t is given by the volume VB of space occupied by it. So the total volume of this body or this system is V at this given point of time, which is t, and it is at the same time, which is t, it is bounded by a piecewise smooth surface S. Okay, so you have the surface S. So at this point, perhaps you would want to know what a piecewise smooth function or a surface is. Okay, so we'll have to do that now. A smooth, before you have a smooth surface or a smooth function, so I'll just call it as a function because you know that any surface can be written as a function. Okay, so the surface of a sphere, for example, can be written as a function fx is equal to x square plus y square plus z square equal to r square. Okay, so this is the surface of the sphere. So that's why I will just call it function for now. Okay, not f of x, essentially f of x comma y comma z. So let me just say what a smooth surface is, and then I'll tell you what a piecewise smooth surface is. And the actual definition is that it can be a piecewise smooth surface or a piecewise smooth surface function. So a smooth function, again this will come up in your lessons of calculus, but I have to do it over here. Smooth function f of x is continuous and has a continuous derivative. Okay, so I will just refer to a one-dimensional function, but you know that for a surface to be drawn you would need a function in x, y and z, just because I want to give a theoretical idea. So if you take up a function, say f of x is equal to x square, okay, this is how it looks like. Okay, you know that. And so fx is continuous. Yes, clearly fx is continuous everywhere, and it has a continuous derivative. So now if you take an f dash x, you get 2x, okay, which essentially is something like this. So f dash of x and x is like this. This straight line, pardon me if it doesn't look straight to you, let me try to draw. Okay, so this is 2x. This is also continuous. Okay, so this is a smooth function. So smooth function fx is continuous and has a continuous derivative. There you have it. Now similarly, a surface will be such that in 3 dimensions, how does the derivative play a role with terms of partial derivative and things like that? You will get an idea sooner when you learn about it in mathematics. But you can just say that if you have a smooth function, then it will be continuous and it will have a derivative which is also continuous. And by continuity, it's the very same definition which all of you are aware, that the left hand limit is the same as the right hand limit at any point. So if x equal to 0 is the point where you want to check the continuity, the left hand limit of the function and the right hand limit of the function is the same. Similarly, the left hand limit of the derivative and the right hand limit of the derivative at x equal to 0 is also the same. So this is a smooth function. Now think of another function, say g of x, and that can be, let's take up a function like this. So this is equal to x. If x is greater than 1, it is equal to minus x if x is smaller than, 0. Okay, so it's clearly continuous. This function is continuous at x equal to 0. Okay, and let's check its derivative. That's equal to 1 for x greater than 0, and it is equal to minus 1 for x smaller than 0. So how does it look like? G dash of x, it looks like something like this. Okay, obviously there is a, it is not defined at x equal to 0, even though the function is defined as at equal to 0, can take either value. Okay, it will be 0, but the derivative is not defined at x equal to 0. So clearly there is a jump over here in the derivative in this particular function. So a piecewise smooth function is made up of finitely many smooth functions separated jump discontinuities. So piecewise smooth function is made up of finitely many smooth functions. Well, this is a smooth function, gx equal to x, and this can be called another smooth function which is minus x. Okay, and hence it is made up of two smooth functions which are separated by a jump discontinuity which is at x equal to 0. Okay, and you can have not just 2, 3, 4, 10, 15, but a finite number of functions like this. So then it would be a piecewise smooth function, and hence by the same logic you will have a piecewise smooth surface. So S of B in a 3D coordinate system. Okay, you know how to draw the three-dimensional surface using XYZ, about conic sections like a cone, okay, or a cylinder and a sphere and so on. So all these are three-dimensional surfaces. So they must be at least piecewise smooth functions, smooth surfaces. So that's what the mathematical definition of a continuum is, that this S of B must be piecewise smooth. Okay, then we move to the last rigid axiom, last rigid the defined entity, sorry, not the axioms. So you have a rigid body is defined as a body in which the distance between any two material points remains the same for all time. So if this is your material body, okay, and it will be called a rigid body, or it will be defined as a rigid body if the distance between any two material points, this and this, okay, or this and this, or this and this. I hope the colors are helpful. And similarly, this and this, any two material points, this distance will remain the same at all times. So if you say apply a loading on this body, these distances will not change. Okay, now how to visualize a body which is not rigid? Well, you can just take a piece of rubber, okay, the eraser which you have to rub the pencil marking, and keep it on your table. Okay, make 2 points with a pencil like this. Okay, and then you please press this, apply a force on this. You will see that this distance has shortened, the distance between these 2 points, because of this load you are applying. Or consequently, if you apply a force in this particular manner, if you try to pull this rubber, you should pull it along the longer direction, obviously. Pull it from both your hands. The original distance between these 2 points will now increase, and hence the distance will change between two or any two material points, and hence this is not rigid. Okay, so this is called a deformable body. In this course which you are learning, you will only be dealing with rigid bodies, though most of the bodies around us and all engineering applications are deformable, but since we are learning a first course in mechanics, we will be only dealing with rigid bodies. Then you may also have to deal with a so-called rigid extension. A rigid extension of a rigid body means it's a massless extension such that the points in this extension move with the body as if they were rigidly attached to it. So if this was your rigid body, okay, it had a mass m. A rigid extension of this body would say something like this. The mass of this is 0, okay, and the points on this extension, all points on this extension like this, will move with the body. So if this body is moving with a speed s in this direction, okay, this will also be moving with the speed s. So this was just a concept which will be used, I think, to solve some of the more complicated problems in mechanics. So the idea of this rigid extension should be clear to you. Do note that putting a rigid extension does not mean that you will change the mass of this body. Okay, that's the whole point. So it should be a massless extension. That's why I have shown that with mass is 0 for this rigid extension. Okay, so these are some of the defined entities. We had time, and then we have the reference frame, then we had a material body in which we defined a continuum hypothesis, then we had the rigid body, okay, and it's not all. There are many other defined entities which we will be learning as we go along in this course, okay. So we have some other defined entities. So this is a position vector r, displacement t. Actually, I should stop putting a number, there are so many, so I should instead use a comma. So position vector, we'll define all of them as we move along. Then you have displacement, we have the velocity, acceleration, of a point. So V P A this is the velocity of p with respect to a, this is the acceleration of p with respect to a. Then you have the angular velocity omega, you have the angular acceleration, okay, the dot represents a time derivative, okay, of a reference frame. So there's a reference frame which we have defined earlier, okay. What is a reference frame is what we have defined earlier, please go and check. So the reference frame can have an angular velocity, okay, it may be rotating, it can also have an angular acceleration. Or a rigid body. So omega and omega dot can be for a reference frame, it can also be for a rigid body, okay. Then you have the moment You can also have MAB, which is the moment of a force about point A okay. Then you can have quantities like the couple or resultant force couple system. All these definitions we'll be learning, okay, so there's no need to worry about if you start getting some of these names. Okay, I can understand displacement, velocity and acceleration was something which you will easily understand. You can have an internal force, resultants, and you can have a momentum. These are all defined entities and hence we will define it. Okay, then you will have a moment of a momentum. About A. You can have the kinetic energy T. Okay, you can have an impulse. Remember the kick on a football. Okay, and you can similarly have an angular impulse. About A. Then you can have the power, sorry, work W, power W dot. Okay, and then the center of mass. Center of mass, I'll just write center of mass. I'll just write COM and it will be by the symbol C. You can have the inertia matrix. Variation. Okay, so most of these quantities we'll be learning in this course. Okay, in fact all of these quantities we should be learning in this course, and we'll define them as we move along on this. Okay, so let's now move to the uh, third topic, which is the axioms. All of them will come when they have to in the process of this course. And right now I'll just mention a few of these names which are relevant. Okay, but don't assume that these are the only axioms which exist. Okay, so I'll just define one, which is the axiom of mass. The mass mb of a body. Remember, B was shown to you over here. Okay, over here. Okay, this was a body B. So the mass mb of a body B will be equal to the union of all the parts. So the body B is a union of all the individual parts. For example, if you have uh, this is your this is the body B, and I am just drawing these parts P1, P2, P3, P4. Okay, so this body B is a union of all these parts. Pi is meaning that you have a union of P1, P2, P3 and P4, or whatever number of parts which you may have. So the mass of this body is a positive scalar whose value is independent of the external actions is a positive scalar whose value is independent of the external actions on the body. See, you have a body B and now you subject it to forces from some directions, or you subject it to a higher temperature. Okay, the mass of this body will not change. That's why it is said that it is independent of the external actions on the body and its motion. So if this body starts to move, okay, you throw a piece of stone into the air and it goes and falls on the ground. The mass doesn't change, right? While it is in motion or things like that. And this mass of this entire body will actually be the summation of all the individual parts of this. Okay, so that means that it will be sum of mass of part 1 plus mass of part 2 plus mass of part 3 plus mass of part 4. Okay, so this is how the mass is defined. The axiom of mass is defined. Then there are many other axioms which will come across, and some of them you would already know. I'll just, for the mention of name, I will write a few of them over here. So we have the Euler's axioms of momentum. The moment of momentum, then you have the Hamilton's principle. I'm just not writing all of them. So you have a fixed point over. The Hamilton's principle, the Coulomb's axiom of dry friction, okay, rolling resistance, Coulomb's law of electrostatic force, Lorentz law of electromagnetism, axiom of gravitational force, Cauchy and Euler's axiom of stress, which normally comes in the second year students for mechanical, civil, and say I don't know, textile engineering students. So only when you do a course in solid mechanics in second year, then you get to the concept of stress. But those are all axioms. Okay. Then there's a Hooke's law. Okay, which tells you that the relationship between stress and the quantity called strain is somewhat linear. You may have heard about this in your earlier classes of physics in your school briefly. Okay, and then you have the Stokes law for viscous fluids and things like that. Okay, remember the terminal velocity. Okay, so of a sphere falling down, and then it achieves a terminal velocity. There's a drag force and then there's a gravitational force, and both of them are somewhat balancing out. So that's the Stokes law of viscosity. So there are lots of axioms in mechanics itself, but we will not be dealing with the axioms of stress or the Stokes law and things like that. We'll be just dealing with the momentum and the moment of momentum. Uh, okay, so that's what we'll be dealing with in this course of ours. So you must know that there are many other axioms. And the last sort of topic is the theorems. They are derived from axioms. Please understand the sequence. We first define the primitives because that's the very first thing which has to be defined. There is no other thing to define it in terms of. Okay, then we define certain entities like time, so clock, the difference between two events, reference frame, and the material point, material body, a rigid body. Okay, based on these defined entities we have axioms. Okay, say the axioms of mass or the conservation of say linear momentum and angular momentum and moment of momentum and things like that. And based on these from these axioms we derive certain theorems. Okay, so say a Newton's third law is a theorem which is defined, which is derived from the axioms. Okay, axioms of force, which you will see later on. Then you will have the impulse momentum and angular impulse momentum principles. Okay, you will have the work energy principle for C. C, remember, was the center of mass. So remember this definition that F is equal to MAC. Okay. Then you will have the impulse momentum, angular impulse. Okay, so many of these theorems will be dealt with as we move along. So we constrain ourselves to motions and velocities which are very small compared to the speed of light. Okay, that's called the Newtonian mechanics, Newtonian model, whatever one would want to call it. And as I've said, for most engineering applications it works. Okay, so if the velocities which we are dealing now, velocity over here can be the velocity of a body, it can be the velocity of a material point in a body. Okay, and if this velocity is smaller than the speed of light, then clearly v by c will be smaller than 1, and v by c whole square will be much smaller than 1. Okay, if a quantity is smaller than 1 and you square it, it becomes smaller still. So unless you have speeds which are, say, less than 30,000 kilometers per second, then you can go with Newtonian mechanics. Okay, if not, if you are dealing with velocities which are much higher, okay, higher than a number, then you have to go for the so-called relativistic uh, mechanics. Okay, so in this one there is a independence space and time. In the relativistic one there is a space-time continuum, so I hope you have heard about those things before. But again, in this course and most of the engineering applications around you, in fact all the engineering applications around you, unless there are some very special cases, you will not be achieving velocities which are comparable to the speed of light, and hence what we learn in this course is good to go. Now obviously there was once a time where it was believed that if there is any speed of any body or an object, it would depend on the frame of reference. Okay, and this was broken down because the speed of light was shown to be a constant. Okay, so since this idea that the speed is actually, or the velocity is frame dependent, was broken down because the speed of light was a constant number all the time. So then there was this need for a new field to study into, and I'm sure there are plenty of courses which you can take up in later years of your study, which will deal with relativistic mechanics and things like that. Okay, so here we will be only dealing with the Newtonian mechanics. So let's talk about now the frames of reference. You can have an infinite number of reference frames exist since any number An infinite number of reference frame exists since any number of rigid spaces move relative to moving relative to one another can be considered. So rigid spaces is the same, I mean the distance between 2 points in the space, okay, which will not change with time, it will always remain the same. So that's a rigid space, and relative to one another can be considered. So if you have, say, a sitting in a car, you can attach a reference frame to the steering of the car, you can attach a reference frame to the ground, you can attach a reference frame to the wheel, you can attach a reference frame to a bird which is flying above the car or anywhere else for that matter. So you can have infinite number of reference frames. So for any body or any frame, you can attach any number of coordinate systems which you want. Okay, and you should also, obviously, since it's a frame of reference, you, other than having a coordinate system and a space, you should have a observer who can observe time between events. So they will all be called the same reference frame. Okay, all these different coordinate systems which you attach to a reference frame, if there is an observer measuring time, they will all be called the same reference frames. Okay, and it can be attached to any rigid body. Okay, so you can call the frames by any name or number, and you will see lots of examples where we have to call them by, say, F, G, T, I, M, 1, 2, 3. Let's draw a few of them. Okay, so this is the Earth. Okay, you have the North Pole, you have the South Pole. Okay, so this is a G frame of reference. Okay, over here it should all have a coordinate system, so I'll just draw it over here. So any coordinate system attached to the ground reference frame is the same. Okay, now if you have a room like this, okay, and say you have a door of this form, this can be called an F frame of reference. If you have the sun, okay, this is the I, sun. Okay, and if you have a vehicle, okay, let's call it as the T frame of reference. It's you can have a rocket like this. Okay, then you can have a mechanism like this, in which, so this is similar to a piston cylinder assembly in an internal combustion engine. So most of the cars and bikes which you see on the road work using internal combustion engines. So you have this piston which is 3, then you can have this cam 1, and then this rod 2. So these are 3 separate coordinate reference frames, so 1, 2 and 3 in this. Okay, so the piston can be third reference frame, and you can see how this mechanism works, right? So this piston, if it moves left and right like this, then this is connected to this over here, and it will be rotating in this particular fashion. So the linear motion of the piston converts this into the rotational motion, and this goes to the shaft which drives the your front tires of your vehicle. Okay, you can also have some other frame like this. Okay, so for all the frames you can have this reference frame. You have to have an coordinate system. Okay, now I am not drawing it on a T, but you could have drawn it anywhere. Okay, similarly for a rocket, anywhere, and for each one of them you can draw anywhere. There are 3 reference frames in this one. Similarly, you will have a I, J, and K, 3 unit vectors. Okay. So the reference frames in this course and in general will be represented as a rigid body. Okay, what would it mean? That the coordinate axes are embedded in it meaning the rigid body. Okay. So I have shown several. So red coordinate systems are what you can see all around. So the most common coordinate system which we work with are called the Cartesian system, which has x, y, and z, something which you are very familiar with. Okay. So I, j, k be the unit vectors in the direction x, y, and z. So let so I'll come back to this definition which we had. Okay, over here, this F1. These vectors are constant. Fixed in F. Okay, F is the frame of reference, and when we say that a vector is constant, it is means that it does not change the magnitude and it does not change the direction. So since I, j, k are the unit vectors, clearly the magnitude will always be 1, but the direction is also remaining exactly the same. Okay, which is shown to you. So let me just draw that over here, I think nicely. So this is the frame F, and you have J, K, and you have the I. Okay, now let me draw a vector A. Okay, so this is the vector A. It will have AX, it should have AY, and it will have AZ. So coming back, let ijk be the unit vectors in the directions x, y, z. These vectors being constant fixed in F, which is shown in the diagram to you, we can say that the di by dt in this frame f is equal to 0. Similarly, dj by dt in the frame of reference is equal to 0 since they are fixed, and dk is also equal to 0. Now if you have any vector which has any vector at time t has components ax of t okay. So ax of t, ay of t and az of t are the components along the I, j and k directions. Okay, you can see the directions over here. Okay, I, j and k directions. So this is with respect to the frame f. So now you can define the frame derivative of a relative to f. So this is defined a dot f is equal to, okay, I'm writing equal to defined so that you know exactly that we are defining it. So dot represents a time derivative, so that means dA by dt is I, j, k are all fixed. So what's the only variable left, which is time? Okay, so you will have a limit of delta t tends to 0. This is how a derivative is defined, over a of t plus delta t minus a of t divided by delta t I, j, k fixed. Okay, I have this habit of drawing a hat over a unit vector, which is actually correct, but I don't want to use it over here just to be consistent with the notation in your text. Okay, so this is equation 1.1. okay, and this is the derivative of a, the time derivative of a with respect to this frame f where I, j, k are all fixed. Okay, now if I, j, k were, and this is happening because if you say apply the chain rule over these, okay, they would all be 0. Okay, so look at this definition. Okay, a of t is equal to axt I plus ayt j plus azt k. So if I had to, okay, uh, really get to this, so I would have done a dot of f is equal to ax dot I, okay, then I would apply the chain rule. So ax, I'm dropping the argument of time. Okay, this would be dot plus ay dot j plus ay j so these quantities are all 0, okay, and hence we have come to this. I'm just putting in a bracket. Okay. These quantities are 0 because they are fixed, okay, and hence, okay, so this derivative which you have seen, a dot f is equal to a dot xi plus a dot yj plus a dot z az dot k, this equation 1.1, this derivative depends only on f and not on the choice of origin. And orientation, axis. The components of a dot f can be given with respect to any basis vectors. What it means is that let's have this frame f, okay, and let's have this blue coordinate system, okay, which is I, j and k. So you can then write a dot f is equal to ax dot I plus ay dot plus az. You can now also have another set of basis vectors, say I, j, okay, and write this as ax dash dot I dash j dash k dash plus ay j, sorry, okay. So when they say that the components of a can be given with respect to any basis vectors, so I'll just show this to you by example. If you have a two-dimensional space like this and you have a vector say 3i Okay, so I'll just write it over here. This vector is a 3i plus 4j. Okay, this is x axis, this is y axis. Now if I rotate this coordinate system such that my new x is lying like this, my new y is lying like this. Okay, so I'll just call it x dash and y dash. In this space, this point will read out as 5i dash, okay, plus 0j dash. So the same vector can be written in the black basis vectors. Okay, then its component would be 3 and 4. If it's written in the red basis vectors, then the same vector, the components of it will now be 5 and 0, and hence over here in general this will not be ax dot will not be equal to ax dash dot, and ay dot will not be the same as ay dot dash. Okay, and the same for over here. In general it will not be true, just like 3 is not equal to 5 and 4 is not equal to 0. So that's the meaning of that. The components will keep on changing, the vector will not change. Okay, this vector will still continue to be from over here till over here in this direction. It's the representation of it will be changing depending on what the basis vector is. Okay. So if you have a scalar quantity, okay, like temperature, and what would be the time derivative of that with respect to this frame f? That will be equal to f dot. Okay. Okay. So this will be independent of f clearly. For a time dependent scalar function f of t, like temperature, there is no orientation involved, and hence time t is the same for all frames. F dot f is equal to f dot, which is independent of time. Okay, so let's now move to the next topic, which is called the position vector. Position vectors of locations. Remember that we had certain entities to be defined, and in which we had said that the entities to be defined like the position vector and displacements. Okay, so we will be doing that. Let's see. The best way to show this. Okay, let's see. So consider locations P, Q, R, S, okay, of a reference okay. So F is the reference frame, and you have to consider locations P, Q, R, S over here. Okay. I'll just draw them in a minute. This is P, and then you have S. Now this is the frame F. So the position vector of P relative to Q is denoted by RPQ. Okay, RPQ, and it is a line segment going from Q to P, which is this one, going from Q to P. So this is the position vector of P relative to Q. Okay, so RPQ is equal to a vector QP. Okay, so if this relative to Q is actually relative to a reference location O, okay, then you would say that the position vector of P is RP. Okay, so I'll just change that in a minute. Let me just come to another one. So you have this point O, this is the fixed F. P. Okay, so that's what it said, that if the position vectors of all points relative to a particular fixed reference location O over here of the reference frame are termed their position vectors. Okay, so the position vector of this is RP. Okay, so this is RP. It is equal to RPO. The idea is that when it's with respect to O or the origin, then the reference is not written, and hence it's just called RP. Okay. Now, some of the things which we can write are clearly RP is equal to RPO is equal to OP. Okay, vector going from O to P. So that's equation 1.2. Now this point Q is written as, this vector can be written as RPQ. Now you know from your own knowledge that RQP will be equal to minus of RPQ. Okay, this is something which you already know. So the position vector of R of Q with respect to P will be the negative of what the position vector of P with respect to Q would be. Okay, and then you can also write RPR is equal to RPQ plus RQR. Okay. So if you look at this particular triangle, RPR will be P with respect to R, so this one will be equal to RPQ, this one, plus RQR, which is this one. Okay, so this is just the triangle law. I mean, you can keep on moving in one direction and you will go to the same point. So if you start off with this point, okay, you say RQR, I'll go here, then I'll go RPQ over here, and then I'll go to a minus RPR, okay, which is this one, and then I'll come back to the same point, to the same position. So that's how you can derive this. And you can keep on doing it for as many number of times. So this will become 1.3. Now using these two, we can say that RPQ is equal to RPR minus RQR. How has this come? Just write this equation, okay? So RPQ will be equal to RPR minus RQR. That's how this has been written. Now PR, so this can also be written in terms of the point O. So this would be RPO minus R. I think I should draw this separately, slightly ahead. This is a good place to write. So this implies that RPQ is equal to R. Okay, this will also be equal to RPO minus RQO. How will this happen if R is equal to O? Okay, so here this point is R, here this point is O, and hence this can be written. Okay, then since we can drop the O part, we will get RQ, RP minus RQ. Okay, or let's take up the other way. Let me just use another ink. Let me just call this as R over here. Okay, so this would be RQR, and this would clearly be RPR. Okay, so you can now see that RPQ, so I don't have to now do this. Okay, I can say that RPQ is equal to this because of the black ink, and RPQ is equal to this. Okay, this is because of the green ink, okay, and the green triangle, and this is because of the black one. So I'll just use a black ink over here. Okay, So RPQ can be written in terms of both RPR and RQR and RPO and RQ. Okay, and this can be written as RP minus RQ. This can also be written as RPS minus RQS. Why? Just to draw another triangle, say this point is S. So this will be RPS, this will be RQS. So RPQ now can be written in terms of this blue triangle. So all three of these vectors can be written either in terms of the black, the green. So what this means is that this vector RPQ, sorry, I should go with the black ink. RPQ is the difference of the position vectors of locations P and Q with respect to any location. Okay, see, we had taken O, we had taken R, we had taken S. It did not make any difference. The vector RPQ was the same. Its representation kept on changing. Okay, so this is always the difference between position vectors of location P and Q with respect to any location. That location was O, that location was S, that location was R. Okay, now once this is done, we can write the chain rule for relative position vectors. Okay, so that can, so first of all this should be called as equation 1.4. okay, so just by looking at 1.3, okay, we can write R PR is equal to RPQ plus RQR. Okay, now since this can be written in terms of O, so this will be O plus, sorry, PR we have just said that this can be written in terms of O, so we'll just be using P is equal to RPQ plus RQ. Okay, just this particular fact that it is the difference between any two position vectors. Okay, and we can also write, now let me draw a diagram over here. So this is F frame, this is O, and then you have this point P. So this point is S. You can So let me just write out all these vectors: R, RS, RSO. Okay. So RPO, okay, can be written as RPQ plus RQR plus RRS plus RSO. Okay, so basically this plus this plus this plus this is equal to this. Okay, so this is the chain rule of position vectors, and this can be called as 1.5. So the closing remarks on this discussion is that a location in a 3D space can be prescribed by giving an ordered set of three numbers called its coordinates. With respect to a triplet set of coordinate lines embedded in the space. So these lines can be either Cartesian xyz, or it can be polar r theta z, or spherical r theta phi, but then there will be three coordinate lines. Okay, so this definition is self explanatory, but then there is this ordered set. This is something for you to figure out. I think this is not the first time you are learning this word. Perhaps it's a good time to go back and check what an ordered set is, and then we'll be discussing the topic ahead, which will be the kinematics of a moving point.